Welcome back to Goliath. I'm here with Lachlan, and we're going to be talking today about Rust and an implementation that he made for the nRF91 using Goliath. How you doing, Lachlan? What are we going to be talking about here today?
Yeah, thanks for having me on, Chris. I'm doing really well. So today we're going to be talking about a little bit about Rust, not too much, and then I'm going to be showing off the kind of prototype of using Goliath and Rust together that I wrote uh, during the summer.
Okay. And what is Rust for people that don't know what it is?
Sure.
There's probably it's an entire programming language, but what's different about it, I guess.
Yeah. So Rust, as you said, is a programming language. Rust is a compiled programming language like C or C++. And a lot of people like Rust because it brings higher level features that C++ has, but also languages like Haskell have, to kind of low-level compiled language like C or C++, um, with the addition of a lot of memory safety features that make it easy to write code um, that won't have seg faults or other, use after free or other issues like that. Um,
So the memory piece is something that's definitely something that I've heard a lot about from you, but also from other people that it's just a lot inherently safer. It's going to, when you're doing weird things with pointers, it's going to kind of put some rails onto you. Is
yeah,
that a fair assessment?
it's kind of like training wheels in a way. You know,
Mm-hmm.
it
But still very
makes you
capable, right?
yeah, it's just as capable. You can do everything that you can do in C or C++ with Rust, more or less. Um, in fact, it's more capable in some ways. But yeah, it kind of most of the time it kind of puts training wheels on you, says, no, you shouldn't be doing that, or you can go and use the unsafe keyword and basically tell the compiler like, this is safe, but you don't know how it's safe, but I know.
Right, right. Yeah. I'm an adult. I know what I'm doing here. Take those wheels off of
Exactly.
me, please. Yeah. Okay. All right. So then, how did this end up working inside of the NRF ecosystem using nRF91, which is a cellular modem from Nordic Semiconductor? How did that kind of all play together with Goliath, and how did you get those two things to work?
That's a great question. So the NRF, the nRF9160 and the other NRF boards have a library that Nordic provides, a binary library that essentially just exposes kind of a Berkeley socket like API that talks to their modem on board. And so there's Rust bindings to that. Someone released that, thankfully, and so it's basically just Berkeley sockets. And so I've used that API in my Rust kind of prototype for Goliath. And so it just uses that to connect to the Goliath servers and write data and receive data, just as you would with doing it in the C implementation. And Zephyr, for example, on the nRF9160 uses the same library underneath.
Okay, great. So were you then interfacing to the Zephyr code that's on there, or directly to the
No,
bindings?
directly to the bindings.
Okay.
Most of the time when you're using Rust on embed devices, you don't need an RTOS because Rust has some good abstraction capabilities built into the language.
Hmm.
So there's no RTOS. It's just Rust running on bare metal, as one might say, connecting, kind of using the NRF xlib, as they call it,
Got it.
to talk to the modem.
Okay. Yeah, and so that actually does bring up another thing that we were talking about a little bit before we started recording. You do need to use a debugger, whereas maybe with some of the examples that we have on Goliath, we use a bootloader so you can load things over USB. In this case, you will need to use a debugger, which you have plugged in via a tag connect 6-pin header that does SWDIO and SW clock, right?
That's exactly right.
Yeah.
There's some work being done on bootloaders in the Rust ecosystem, but it's not ready
Mm-hmm.
yet.
Okay, cool. And then, so there's the safety element. Is there any performance benefit, performance hit from this sort of thing, or kind of too early to tell for using Rust?
It's a good question. There's a just comparing Rust and say C or C++, they're going to be more or less the same performance-wise. Rust, most of the checking that makes Rust safe is done at compile time, and there things like bounds checking arrays is done at runtime because it has to be. Um, but it's normally not a significant performance issue. There are other things about Rust, like having better aliasing information that it can pass the compiler that make Rust faster than C or C++ sometimes.
Cool.
But in embedded systems, it doesn't really matter.
Got it. Yeah, like you said, I mean, it's interfacing to this what is effectively like a binary blob, right? That's the POSIX bindings,
Exactly.
and so you're getting what you're getting with the modem anyways, and then you're kind of writing code around it and interfacing like that.
essentially.
Yeah.
Yeah, to be a little more specific, there because Rust has generics or type parameters depending on what you want to call them. A lot of stuff that might be virtual calls in C, for example, calling function pointers ends up being inlined in Rust. So performance might be a little bit better in some cases, but it's going to be pretty much the same.
Okay, great. So then the other piece of this is interfacing to Goliath, of course, and our transport mechanism is CoAP. So you had to kind of dig into that side of things. What did it take then to, you're interfacing now with the modem, but then you're trying to pass stuff back to Goliath. You had to do some CoAP stuff as well?
Yeah, so that's right. Goliath uses CoAP, or at least our first protocol that we support is CoAP.
Say that wrong about transport layer versus protocol. I'm
I I
I'm a
I
hardware
don't think you
person.
said it
Let's be
wrong. Yeah,
okay.
no, I
Great.
wasn't
Yeah,
trying
yeah.
to be pedantic or anything.
No, that's great. I mean, this is great. This is, I mean, learning new languages like this and learning stuff from people implementing it. I think it's really, it's enlightening, right? It kind of shows how things are built anyways. I feel like when you have SDKs, when you have things that are handed to you from vendors, like Nordic might hand you a dev kit or something like that, my first thing is just get something blinking, but there are so many layers of abstraction below, and it seems like what you've done here is you're kind of starting from that, you're looking at what's the smallest atomic element, which in this case is that POSIX binding, and then you're building up, which is super cool. I think that's
Yeah,
really, it's enlightening. It helps you understand the platform better.
yeah. Something I love about kind of using Rust Embedded is lets you easily peel away these layers of abstraction. So it seems like there's less hierarchical layers when you use Rust Embedded versus something like Zephyr, or any other RTOS, which is essentially a full operating system. So
Mm.
there are a lot of layers of abstraction, even if they're not
Yeah.
performance issues or anything.
Right. It's more, it's tougher when things go wrong. I feel like that's one of the
It's it's harder.
downsides.
The big thing for me is it's harder to hold it all in my head at once.
Yeah, that's true. That's true. Yeah, and you get benefits from something like Zephyr. You get the benefits of, well, you don't have to think about networking if everything else is working right. If you're within these ecosystems and these if you're in the same playground that other people have played in before, yeah, you get to just use the stuff that they've started with, and that's really I think one of the primary benefits of Zephyr. But like you said,
Definitely.
stripping it back, you get to understand more of it, and you might have a simpler app at the beginning, but then you can kind of build out from there as well.
Yeah, there's a balance between abstraction and
Yeah.
also ability to actually understand what's happening.
Cool. Well, let's try and understand what's happening. Can you show us some of what you got going on here?
I'd love to. Yeah, I have it up right here in VS Code. Let me just move this to the side. So, like, so this is basically regular Rust embedded right now. Rust embedded has Rust in general has a standard library and a core library, and the standard is essentially extensions on top of this core library that let you do things like file operations and stuff that requires an operating system. But on Rust embedded, we have core, which has a bunch of stuff that seems like you need a standard library for, but it's doesn't require an operating system or allocation, so you can just use a lot of this stuff. And there's some further down that uses that kind of stuff. So this is the entry point. It's using this library called Cortex M RT, this crate as it's called in the Rust ecosystem, and which just sets up the right kind of interrupt like vector installations and the right like basically sets up an entry point at the right location in the binary, um, so that it gets called when the MCU boots up. So this is some Rust embedded stuff. We're getting kind of the peripherals of the device. What this does is it takes ownership of the peripherals so that um, our code or some other library that we're using, but kind of is hidden, can't take the peripherals and screw up what we're doing at the same time. That's a big thing in Rust is ownership and borrowing, and so you can kind of be sure that you own something and no other code can use it while you own it. This is just setting up some heap stuff, which we need for some of the CoAP stuff. And then this is some interrupt handling, which we need to be able to
I
talk to
see
the modem.
unsafe flags here. It's almost like Pee Wee Herman, and like, ah, you know.
Yeah,
So
I mean,
when you
this is like
see
hold my beer,
yeah, when you see unsafe here, so what should people? I mean, so it looks like you're doing
Yeah.
Interrupt controllers, right? NVICs are
So
non-maskable interrupts.
most a lot of things don't need to be unsafe because you can write zero cost abstractions around them, which is kind of a common term in Rust and also C++. But something like interrupt handling, kind of at the lowest level, which it's here, it's not abstracted away, does need to be unsafe because you can totally break things um, if you screw it up. There's this dumb workaround thing, which is just an issue with the nRF9160. You need to write this particular value to this particular memory address.
Yep.
Um, you see those things all the
That's
time in
right. That's
embedded.
right. They're like the magic. They're like the unlock key almost.
Yeah, and so there's some abstractions that I'm using from embedded HAL, which is this crate in Rust. It's used for basically every Rust embedded project. It's a series of traits, which are essentially also called protocols in other languages or classes. Not really classes, kind of abstract classes. And so you have like an NRF HAL implementation for, say, the STM32F4 or the the nRF9160. So you have embedded HAL implementations for all these different MCUs and sometimes for whole boards because sometimes boards provide more peripherals than just the MCU itself. And so something like this, it's a delay. It basically uses the timer that's available on your embedded system so that you can just call like delay for this number of milliseconds. There's some more stuff kind of similar to that within here. There's this is
As you
logging.
as
Oh
you're
yeah,
developing this sort of thing too, I mean, so are you working alongside the datasheet for the part itself, or are you working alongside the library, the crate for the HAL, or how are
that's
you looking things up? I guess.
that's a great question. So yeah, I when I'm developing for a device, whether using C or Rust, I'm gonna have the data sheet for that MCU kind of on hand or minimized. But also, a great thing about embedded Rust is because of the strong type system and whatnot, is the embedded HAL crates actually enforce at compile time that you don't use the wrong pins for peripherals or that you don't kind of screw things up in a way that it can check. So like each pin is a separate type. And so you can create like an SPI, if you're using SPI, you can create like an SPI peripheral and the datasheet shows that SPI1 can use this set of pins or that set of pins or this other set of pins. And using the type system, it enforces at compile time that only those pins, only those few sets of pins can be used to create that particular SPI peripheral.
And that's enforced by the HAL itself. Is that right?
That's enforced by the type like by the types that the HAL
I'm just
uses or the HAL
I'm wondering
implementations use.
who put that in. Because
Yeah,
I've
so that's like the HAL implementation uses. So like the STM32F4 um, embedded HAL implementation does that, and most others do, but they don't have to. But it's something that the implementers can do that make this stuff really easy. What's very nice about the embedded HAL ecosystem is that most of these crates are auto-generated from SVD files that are kind of provided by ARM or various other vendors. So it auto-generates the HAL. So a lot of the work that there's really not much work that needs to be done to support new boards or new MCUs because it's all auto-generated.
That's great. Yeah, because I mean that's one of those things where if you get to the point where someone typed in the spy, spy one was pin, spy one SDO was on pin 44, it was actually 45. It's like getting all the way down. That's another abstraction thing where you get all the way down to the bottom. You're like, oh my god, who typed this in? And then you realize, well, then I realize it was me. But it sounds like with that SVD thing, it's kind of from the vendor, and yeah, that would be checked many times
Yeah,
over.
it's the vendor, the SVD file, the data sheet says that this can only be used for these pins can only be used for that peripheral. So it can be reflected in the type system, which is great. There's nRF stuff here, initializing the library, doing modem things, installing the PSK ID and PSK, which are how we authenticate devices with the Golioth backend. These need to be installed before the modem is turned on, and then they'll be used when establishing a DTLS connection with our Golioth backend. Turning the modem on, connecting to LTE, and then it runs this function down here with that that kind of delays type, that delay thing that I had earlier, which, as you can see, implements this trait called delay milliseconds. So it's just saying it can delay some number of milliseconds, and it receives U32, so 32-bit integer, unsigned integer of milliseconds. Yeah, here is the really interesting part. This is kind of starting up the connection, that Golioth, and then the Golioth struct, and then the new function on that opens up a socket, establishes a connection with Golioth, and I can show how that's implemented. It's basically just here. Establishes a DTLS socket with those credentials that I installed earlier, DTLS, and then it connects to Golioth essentially. So that's essentially just that. And then
I mean, that's not many lines of code, to be honest. I mean, that's
no. Yeah, and let me talk about something really interesting here. As you notice this, perhaps you notice this question mark here, and it's also here, and you can see it very often, kind of very commonly through a lot of this code.
And so usually that's in my comments. There's like, "What am I doing here?" Question mark. It's a note to myself.
Yes, same here.
What was I thinking?
In this case, it's like an error propagation thing. So instead of exceptions, Rust uses its enum types as error. So the result type here is this kind of enum that's in the standard library, and I could just jump right to it. So it's just a enum that's generic on the value that it the type when it's okay, and then the type when it's an error. And so it can be okay T or error the E type. And so when it's okay, you can unpack it into the right. You have to unpack it into one of the values, and Rust has various syntax features for unpacking enums in like a safe idiomatic way. But what this does is this DTLS socket new type returns a result error. So this question mark just says, okay, that's returning an error. So if it's an error, I'm going to return an error from the function that this is in. So
it's like throwing it upstairs. It's like, well, something happened down below, so I'm not gonna let you actually connect now.
So it's basically as easy to use as exceptions, but it doesn't. It works like exceptions aren't really going to work on an embedded system without a lot of elbow grease. So it's just makes it easy to use, but it's kind of different. And then you can see I'm returning okay, the kind of this type, the self, with the socket, the DTLS socket, which is kind of, it's a field there. And then back to the main thing. I'm doing this using this great library in Rust called SerDes, which is used throughout the Rust ecosystem to do serialization and deserialization. And what you do is you just kind of add this attribute, this deserialized attribute, to your struct, and it automatically kind of implements the deserialize and serialize, and then but you don't have to tell it what format it's going to be serialized or deserialized into or from. You can do that later, and it just gets monomorphized into a very efficient serialization or deserialization implementation. Monomorphized, inlined, same thing.
And that's because we have a big string of data coming from or going to the server. Is that the reason for serialization, deserialization?
That's right. Yeah. So when I call this Golioth.LightDB get function, what it does essentially is sets up in this case JSON, but we can also use CBOR like block with some various data in it, and then it puts it into a CoAP message. Basically, it compiles, adds the CoAP headers and all that kind of stuff, and then it just kind of dumps that into the socket, which is already connected to Golioth, and so it kind of goes upstream, and then it reads from it, and then Golioth will send the data back, basically with the result, which in this case is going to be some JSON or CBOR, but in this case JSON, because I've set it to use JSON, with this, basically that can get deserialized into this type.
Cool. Yeah, that's great.
Yeah.
And then is there like something that is actually setting up all of the formatting that needs to happen for that JSON? Is that some other function somewhere, or is that just this deserializer?
I'll show you. Yeah.
Okay.
In LightDB get, in LightDB get, it makes kind of I have this function that essentially just makes a raw get request to a particular path. So it's just sending a CoAP message upwards that says, I want the data at this path in LightDB. And then it receives this payload, which is essentially just a vector of bytes, a list of bytes. And then we use SerDes JSON, which is a JSON format serializer, deserializer that uses SerDes. And we just do from slice, which is just some.
So it just like takes off the curly brackets and the parentheses, and it basically just kind of separates out keys and pairs, right? Or key value pairs.
Yeah. Well, it does. It'll parse things as integers, or it'll basically do all the parsing necessary to turn really this JSON struct into a native struct, a Rust struct. It's really neat, and it works the same way. Works the same the other way. Here in LightDB set, I'm making this function generic on. It kind of takes a type that implements serialize, and then you can see here, I'm just setting the payload of the CoAP message to be a vector of bytes that's produced by SerDes JSON TVEC, which just takes this type and converts it to JSON, a byte, just like the byte string from the serialization from that struct to JSON.
And the .d there, I see the .d slash a couple lines up from that. That's also how we interface to the device characteristics for various things you might have. You know, you could have different LEDs. That's, I think, in the LightDB demo, we have 4 LEDs. And so there's LED 1 through 0 through 3. And it's at that same .d slash, right?
Yeah, it's like the prefix for the path, to say that this is this is the database, not the stream or something else.
That's great. Yeah, that's really clean. That's really nice.
Yeah, I love about this is it's kind of really clear what's going on, but it's also really efficient. So here, basically the same thing. I'm setting this value and I'm just passing in this struct. You know, just the counter has I as a field, and it just gets passed upstream. It gets serialized in JSON and passed upstream, which in that function that I just showed you. And then I'm delaying 5 milliseconds. So it's really clear what's going on here. It's very straightforward, like when you look at this code. But it's also super efficient, and it's no less efficient than a C implementation would be, but it's a lot clearer.
Yeah, that's awesome. Yeah, that's really cool. And I mean, so this specifically does not use Zephyr either, right? So that's another thing that's different about this, is that we in Zephyr, so if people watch the Hello demo, which is what's in our getting started for both nRF91, which we're using here, or the ESP32, it's using basically the logging capabilities to do the same thing that Lachlan's doing here. It's just sending a log message through Zephyr, through the various levels of abstraction. We plumb that together with the network at some point, and then that goes up to the Golioth network. But this is kind of doing all that stuff outside of it and still pushing it through the interface, through the nRF91 to the modem and out to the Golioth network. But it doesn't have all the things that Zephyr does to do that same formatting around CBOR and or JSON in that case. So yeah, this is cool.
Like Zephyr has libraries for doing this various formatting of CBOR or JSON. But in this case, I'm just using the library that Rust uses, that almost everyone in Rust uses for deserialization, and it works without an operating system, without any of that kind of stuff. It just works on bare metal, which is really neat. Something I love about Rust is how that's possible.
Okay, this is great. So yeah, I mean, this is a really cool implementation. Thank you for walking us through this. Where can people find more about using Rust with Golioth and Zephyr, or without Zephyr in this case, and on the nRF91?
Yeah, so we have this prototype implementation, which I'm showing right now. It's going to be open sourced in the near future, so we'll talk about that on Twitter or on LinkedIn to kind of point to that, and it'll likely also be in our docs, just saying like, we tried this, we're going to expand this in the future, but here's kind of what we had so far. In addition, actually, there's in the README, it talks about what needs to happen in the Rust ecosystem for this to become a real, like an actual product. like networking support in Rust for embedded is a little immature right now. There's some other things that kind of need to be sorted out first, but kind of there's a few different things, like there needs to be networking read write kind of networking traits available on embedded Rust and a few other things, and then this can be expanded to support more than just the nRF9160, but any board with kind of a Rust embedded HAL and a network stack that's available through Rust, and that's basically, that can be pretty much anything. So
Okay.
so I
Awesome.
think it's really exciting.
Yeah.
But this is early days. This is just a prototype.
Okay. Yeah. Well, prototypes are great though. I mean, it shows it's possible, and like we talked about, it also helps you to show, as it's stripped down, as it's a little bit simpler than it might have been otherwise, and allows people to build up from there. So this has been really
Exactly.
great.
Thanks.
Lachlan, where can people find you online if they want to talk more about
I'm in a
Rust?
couple different places, but probably most predominantly I'm on Twitter and my handle is @LachlanSneff.
All right. No.
So I talk about Rust, embedded stuff, all sorts of things. So
Okay.
feel free to follow me.
Yeah. Let's see if I can get this on here. Lachlan Sneff. And there we go. Is that going to work? I'm not sure that's going to work. There we go.
There we go.
@Lachlan
Yeah, perfect.
Sneff. Yeah. All right. Okay. Well, thanks so much, Lachlan, and I'm looking forward to future Rust experiments.
Thank you. Thanks. It was great to be on.